What's up, everybody? Today we're going to talk about a very important subject, which is linearization for a given nonlinear dynamical system. Okay, so let me just say a couple of words on what we're going to do today. We have a nonlinear dynamical system, okay, and has input states and output, okay, and then we will try to find the equilibrium points. When we say equilibrium points, and if the system is not autonomous, and meaning there are inputs and of course there will be outputs, right? Well, we will need to determine equilibrium points, and equilibrium points for states, for input signals, right, control signals, right, and output signals. And then by using those equilibrium points, we will linearize and obtain state space representation of the linearized in the given equilibrium point dynamical system, right? So we will have A, B, C, and D matrices, okay? And by using those matrices, we will construct a linear plant, okay? Linear LTI dynamical system. And by using this plant, we will design a K controller, okay? It can be a reference tracking application or just for regulation purposes, okay? And then you will test this control, test this K object, okay, on given nonlinear dynamical system. You might like to do that in simulink probably, okay? And now we are going to talk about this. This is our agenda today, and here linearization, and this is the structure of the given nonlinear dynamical system, okay? This is again state dynamical equation which explains the evolution of the states, right, as t changes. And this is output equation, and depending on the cases you might have only a state regulation problem. So you might like to assume first of all, hey, I like to assume that I have all states available to me, right? I have the capability to measure all the states, right? Okay, so I don't want to constrain myself in that way. Maybe you like to start from a simpler problem and then you like to build on, right? Okay, so this is our starting point, and we need to find equilibrium points, okay? And how we are going to do that? First of all, this is our state dynamical system, state dynamical equations, and probably you like to find your equilibrium point, or I need to say, I guess, trim points, right, as an equilibrium point. And anyway, let's not focus on trim subject. We need to find equilibrium points, and the objective is that all the states must be in steady state condition, meaning they don't change, okay? They don't change, translates to their time derivative is equal, 0. So those terms, they need to be equal to 0, okay? So the problem translates to, right, hey, find x and u, right, such that this term is 0, right? And there are like n terms like that. So how can you do that? I mean, it is basically an optimization problem, okay? So, and before moving on, I'd like to say a couple of side notes. You might like to have some constraints on your optimization problem. For example, for your system, for your planned nonlinear dynamical system, and it can be a real system, right? And you have some information, you have some expert knowledge about that, and you wanna there might be some specific reason for you to, for example, set one of your inputs to a specific point, okay? Or maybe you like to constrain your, input signals. Maybe you like to do that like inequality constraints. Maybe there is some, maybe your motors cannot generate more than 5 Newton, right? So you like to constrain that. This can be a reason. And this type of objective translates to, right, absolute value of u1 minus 5 type of additional constraint. And actually, yeah, it's a constraint, but we like this term to be 0, right? Meaning we like it to be minimized and see what happens, right? And so we can just, stack all the terms. Let's say t1, t2, dot, 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 tn, right? These are all scalar, right? Minimize that and see what happens, okay? So, all right, we can just, for example, first tn term might be your, x dot terms, and after that you can impose your, input related constraints, and additionally you will have, right, output related constraints, and you can just stack them up together, and the resulting expression is the term that you like to take it as cost. And by changing x and u, you like to minimize this cost term, okay? So let's move on and focus on the output constraints. Maybe you have some constraint, I like my second output to be equal to 20. There can be, again, specific reasons for that. For example, not that I know much about aerospace engineering, right? But maybe you like to fly at some altitude, right? Maybe 2,000 meters. Maybe you like to have some rudder angle. Well, not rudder angle, but yeah, altitude is a better example, I guess. Yeah, maybe you want this y2 is your altitude, and you like your altitude to be equal to 2,000 meters, right? Or something like that. Or maybe you just regularize and you want it to be, 20. Or maybe between 20 and 10, maybe that can be the case as well, right? So again, this is your y2 expression, g2, okay? And you want it to be 20, and this is the term that now you like to minimize, okay? And absolute value, of course, you can just square that too, okay? I wanted to use absolute value because I see in the Matlab trim function and lin mode function, I guess. And maybe I should write that, trim and lin mode, okay? These are Matlab routines to obtain equilibrium points, okay? Yeah, this expression also needs to be minimized. So all the terms that you like it to be 0, just and they need to be, again, scalar, right? Stack them up together, right? And minimize that, okay? So here, this is our starting point, and when we find x equilibrium, u equilibrium, and output equilibrium, right, this expression, state space representation of your linear dynamical system, is the term that you like to obtain. And this is just a, something that we are really familiar with at this point. This is a basic formula, right? And by the way, f and g, they can be incredibly long and complicated, right? And so I'm explaining that abstractly, and of course you like to use some optimization tool. Let's, for example, fmin, con, right? F minimize and constraint. There will be some constraints. Okay, you of course you like to use some type of routines, right? And to be honest with you, even if your problem is like a really small one, I think you should, if that's your job, by the way, right? If you do that in professional life, you need to, by the way, learn this type of processes, right? And if you're just taking a control course or something, yeah, okay, I want you to have fun, okay? And okay, this is it, right? This is our nonlinear dynamical system, and we can just express the problem in that way, right? So we call this like delta u, right? Maybe say, wait a sec, x equals x equilibrium point delta x, okay? So x, I call it large signal, okay? And x equilibrium, I call it steady state component, okay? And delta x, small signal component, okay? And again, u equals u equilibrium point small signal part of u, right? And also same goes for, you know, output, maybe reference signal. I guess that's it, right? So maybe I should delete all of them and just write large signal, right? This is large signal itself, right? And steady state component, right? And small signal component or part, okay? All right, so now we establish our, you know, terms, and here this is small signal, right? And this is equilibrium point, or I'm sorry, this is steady state part of it. And if you add them up, right, what you get like large signal u, large signal input, okay? And you need to input large signal and you will get large signal output, okay? And by subtracting steady state part from a large signal, you would get like small signal, okay? And small signals is our focus in control design aspect of the, you know, general control problem. And here just I draw a, you know, red box, and here, so this is our problem now. This is our problem, okay? And we talk about the A, B, C, and D matrices, their, you know, formulas. And as soon as you have that established, just check them. And this is, I call it plant, right? And this is a linear dynamical system. As soon as you have that, as soon as you have A, B, C, D matrices, right, as numbers, okay? And just check the poles and zeros, okay? And the important part here at this stage, you like them not be located on j omega axis, right? Because that will, you know, that will create some complications, okay? And of course, after that, if there's no poles and zeros on j omega, maybe I should write that no, you know, poles and zeros on j omega axis, okay? And this is the thing that you like to, you know, check. And if there's no poles and zeros on j omega axis, right, or imaginary axis. You like it to check, you know, you like your system to have some controllability ability, right? It's not 100% necessary, but I would advise you to, of course, check controllability and observability, right? Why did I say not 100%, you know, necessary, critical? Because, I mean, your system might not be controllable, but it might be a stabilizable system, and that's still suffices, right? Or of course, depending on your, you know, control problem. But at least these are some properties that you like it to check. And of course, your system might not be observable, but it can be detectable, right? Okay, and by the way, we have talked about this, right? Okay. And so I'm not going to go over them. Maybe you like to check if that's a passive system. To be honest with you, I'm not 100%. You know, familiar. I don't want to say familiar, but yeah, you know, accustomed to this type of passivity based designs. I'm not 100% accustomed to them, right? And but it is a property, right? And maybe you want to test if your given nonlinear dynamical system is passive, right? And maybe I'm not again 100% sure, but maybe your linearized, maybe you might like to infer some information about the passivity by looking at the passivity property of your linearized LTI, you know, dynamical system, and again you'll like to design a, you know, I just written 2 degrees of freedom, but yeah, you know, some type of controller. You like to design it and check the, you know, TZW. Dynamical systems sigma plot, right? And by looking at those, right, you like to get some information about the original system you have, right? Okay. And this is the, again, controller design aspect. Okay. And here, this is large reference signal. This is your steady state reference signal. Okay. And this is your small signal part of it. Again, small signal, reference small signal output. I might be, you know, I could have written just, you know, delta E to indicate that's small, right? Small E. Okay. But it's, I mean, once you get the term, once you are familiar with the terminology, you kind of know, you kind of get the point, right? You would get the point, and you don't need to, you know, stress all the, be a, you know, terminology Nazi about that, right? Okay, so all right, this is controller, and here you input the small signal input, small signal control, and small signal output signal. Okay, and here maybe, yeah, it would be a better idea to, you know, compare them. And this is your linearized plant, right? And this is your true plant, nonlinear dynamical system. Okay, so you can just see the, you know, familiarity. You just design your K, right, and then test your K on the real nonlinear dynamical system. Okay, of course you will like to have some H infinity, right, or mix sensitivity, mu sensitivity type of control algorithm to design a controller. Okay, so this is like the tutorial part, and now we're going to focus on I think, in my opinion, a really beneficial example, right? Really, it's going to be a really important example, and after I upload this video, right, tutorial video, I'm sure that I will watch that video, or I will refer some parts of it in the next years to come, right? Because I mean, a lot of people explain this linearization and then contour design, but I feel like there's always some parts of it, you know, they kind of miss out, or they don't, you know, they see as detail and they left it out. Maybe due to their, you know, professional lives and due to their applications, implementations, they don't need some, you know, details, some informations. So, okay, and that's why I made those videos, right? I started making those videos, and right, because yeah, this is not a complicated example, and as in addition to that, furthermore, this is not a extremely simple example that would think you to, you know, or that would lead you to think about, hey, this is very simple and straightforward. Actually, it's straightforward, but if you know what you're doing, right? Okay, so this is a second order polynomial here. This is a second order polynomial nonlinear dynamical system. Okay, all right, so let's maybe get some another curve. Okay, there are 4 parameters, right? A1, Q1, or Q1, Q2, Q3. Okay, all right, these are 3 by 3 matrices, and there's like two input signals, and some constant input signals in a way, but of course constant terms. Okay, maybe this is a gravity term or something. Okay, so it's always there. Okay, so, and in addition to that, you don't like it to be considered as a disturbance signal, right? You just, hey, this is there, right? Okay, so, and I think the problem here in the, you know, nonlinear dynamical system control, I feel like the biggest starting problem is that most of the, you know, in the books, of course, right, whenever they do some linearization, there's an inherent assumption that you by the way, they only talk about the autonomous systems, right? They often cover the equilibrium point where, you know, all the states equal 0, right? The origin equilibrium point, right? And of course, some system might be like that, but it is beneficial to, you know, cover, let's say, equilibrium equal to or something, right? Not the, you know, origin case. And this is not the origin case. This is not a straightforward example. And I specifically constructed that example, and I spent like 3, maybe more hours to find a really, you know, not so simple but not so hard example. And I couldn't, you know, I look at most of the nonlinear control and also the, you know, control books, modern control books, and then I decided to, you know, construct my own system. I just, you know, I will talk about how I generated that system, nonlinear dynamical system, and after I solved that, I thought it would be a good idea to, you know, record some tutorial video, you know, record, and maybe in the future I will again refer to this video to, you know, refresh my memory on some stuff. And okay, so after all those introductions, A1, Q1, Q2, and Q3 matrices, these are numbers, okay? And 3 by 3 matrices, these are, okay? So there will be like 4 matrix, okay? These are numbers, and I'm going to tell you what those numbers are. Of course, you can, like, you would like to maybe generate them randomly, okay? Yeah, all right. So x1 dot, x2 dot, x3 dot, okay? And here, just the linear terms of the states. And here, maybe look at this closer. And this expression, it can be something like this: q1 square, maybe 3, right? 5 times q2, q3, okay? So, and maybe q2 square, okay? the second order terms, right? Like, for example, all the first order terms, right, and second order terms in that matrix, and some maybe zeroth order, terms. Of course, don't call it that, but constant terms. And these are your input signals, U1 and U2. And that's why this is I think, really good example, because there are like 2 input signals, 3 state signals, and 2 output signals. Okay, so this is not straightforward. And first of all, you want to find, this is, but before saying that, we are going to find equivalent points, right? This is the dimension, right? And here states, and of course I could have written something like that, right? But I wanted the problem we have as a, not so hard one, right? So most of the problems, I feel like you like to, have that type of C matrix, right? I mean, it is still holds, right? What you're going to learn in this problem or in this video, they are going to still hold for most of the, because I wanna, leave myself some disclaimer room, most of the, nonlinear dynamical systems. Okay, so this is nonlinear dynamical system, and here this is the parameters, and what is the example is all what? Given a system, all right, find equivalent points. This is objective, right? Okay, and in real life, your first objective is to just find the equations of motion. All the nonlinear dynamical system represent your system in that, standard form. And second, find equivalent points. And third, find the linear dynamical system, right? And fourth, design a linear controller. And your last objective task, maybe, design your cache, design your controller, and test it on the true, quote unquote true. It will still not be a true one, right? The true one is the real physical system in real life. Okay, and just check that, check the stability, check the performance, that type of specifications. Okay, and this block diagram is our, maybe I should get that down a bit. Okay, and here reference signals 0, 0, right? And this is a regression problem. And by the way, whenever you have that type of, small signal, large signal type of nonlinear dynamical system control problem, often, not every time, but often your reference signal is like 0, okay? Because output equivalent point is your reference, right? Okay, so that's the main reason why that's the case. And this is your error. And again, 2 inputs, 3 states, right? And 2 output signals. Okay, and your controller generates 2 small signal parts of the input signals, and you have equivalent points of them, and you add them up, and you have large input signals, and you input that large input signal to your true nonlinear dynamical system, and you will have large signals in large signal form, output signals, and your subtract equivalent or steady state component of your output signal, and you will have small signal component of your output signal. Okay, and this is your control problem. All right, now we are going to focus on that, and we are going to look at the Matlab codes, and I will share I will share. Just look at the GitHub page, the link in the description, okay? And I will supply, there will be a folder, and in the folder SLX, sorry, right? The simulink file and .m, the Matlab script. This code will be in that script, okay? And what was it again? Yeah, and some document file, right? And just what I explained will be in that document file. And okay, so you can download them, right? I would urge you to download them, okay, if you're interested. Okay, so first of all, we have 4 matrices, and you can just generate them randomly, and of course they need to be like 3 by 3, right? And this is randy, right? Generate random integer, and this is minimum and this is maximum values, all right? The range, their range. And after you have your matrices, you can just, you know, for, you know, some, you can just store them in that way in your parameter object or structure. And in Matlab it's called struct, okay? And object without any function, so that type of data types. And the reason why you would like to do that, because it looks simpler and your code would look, you know, clean. And okay, so what are we going to do? All right, maybe let's remind ourselves. This is the problem, okay? And this is the problem in explicit form, okay? And just minimize by using or by tuning x and u, and minimize those expressions, okay? Maybe your x1 is x1 square, x2 dot equals x1 plus x3 cube plus u, maybe, right? In that case, your equilibrium point problem is this. And maybe I should be more explicit about that. x1, x2, and u, right? And okay, I'm just, you know, copying that. Okay, this is your problem. And if the cost is really close to 0, the corresponding decision variables are your equilibrium and u equilibrium, okay? All right, okay, so that was a small example, okay? And by the way, here those nonlinear dynamical, you know, expressions, they can also include terms, like we can call them parameter, all right? Okay, so to facilitate what we are doing, right? Okay, this is ODE function. It has nothing to do with that, but I only wanted to here include it in as comment, because this kind of tells you how you would use some function with function handle, right? Okay, so for example, this function takes 2 arguments, right? But fmin_con is only going to focus on z term of it, okay? Just only focus on this part, and this is some constant that I supply, right? Just cost fun1, okay? So it normally takes z and param terms, but I'm saying I'm going to supply you with the param terms, and you only focus on z and give me the cost. So basically consider this function as that tune z, right, to minimize cost. All right, I think that was a good information, and you would also use that type of mentality in all kinds of optimization problems. All right, and okay, fmincon is the function. Okay, and by the way, why there is a z? Yeah, let me explain that as well. So for example, this is a good simple example, I guess, right? This is your problem, right? And that I made a mistake, x2 cube, right? Okay, because there is no x cube, x3 rather, right? Okay, so you can, just to simplify, right, you can say z1 equals x1, z2 equals x2, and z3 equals u, right? And so you can just indicate that problem or represent that problem as minimize z, z1 square, here I'm just copying that term, z1 plus z2 cube plus z3. And now, I mean, it looks simpler, right, compared to that. All right, and in the code as well, it makes things a lot easier just to have that type of strategy, right, or naming convention. Okay, so the important part here is the cost function, and we are going to talk about the cost function, what this cost function is. It is a function that we written, right, to explain our both nonlinear dynamics, right, and also some, we talk about some input and output constraints, right? So all the cost, all the information is embedded in this function, custom function. Okay, all right. So, and this is, since we have like 3 states and 2 inputs, we have 5 decision variables, right? And you need to supply some initial points. Okay, just give once. Okay, all right, if you don't have additional information. Okay, whenever you have z, and by the way, please check the cost value corresponding to that final decision variable, right? And that needs to be really close to 0, right? Like 1e minus 7 or something. That needs to be close to 0. Okay, if not, you will get some errors down the line. And first 3 of the z vector, first 3 entries, x equilibrium, right? And after that we have u1 and u2. Okay, all right, and let's look at the cost. Let's look at this function now. This function, this function. Okay, so parameter is the term that we know, right? Maybe I should delete all of them. Okay, I keep some notes to remind myself. All right, yeah, I'm going to delete all of them. Okay, so just recover a1, q1, q2, and q3. I mean, just recover your parameters, right? Because you need to tune x and u terms, right? Parameter terms are constant. Okay, and you will need parameter terms because you will have, remember, and maybe p parameter, right? You want to find steady state terms, steady state point, and so dynamical equation is something that you like to, you know, have in your cost function, basically. Okay, get the first three entry of your decision variable vector z is your states x1, x2, x3 here. Okay, and fourth and fifth are your input signals. Okay, and also just store them in that notation to make it simpler, facilitate some operations. And this is, you know, linear terms. These are our second order terms, right? This is like constant terms, and this is input terms. This is x dot equals xu. This is our nonlinear dynamical equation. This is, we know this, right? This is given. Okay, meaning a1, q1, q2, and q3 and their parameters, they are given, right? Okay, and we don't have any additional constraints on u and y. By the way, if we had this f vec, right, like we could written something like this. For example, I guess x2 minus 10, right? Maybe you want your second state, and this can be a, you know, your first output or something, to be really close to 10. Maybe you like to obtain a steady state or equivalent point close to that location, right? You would stack them up. Okay, we talk about this, and this is a simple example and very important one. And just take the 2 norm of that, because this is f1, f2, f3, right? All of them are scalar, but this is a vector. This is a 3 by 1, 3 rows and 1 column, right? Vector. So take the norm. Okay, after that I'm just explaining the code, right? I will just explain that again in the Matlab page. Okay, so clear vars is some command that delete, or for example, we are familiar with clear, right? Delete all of the variables stored on the workspace except these variables. Okay, this is like really simple but useful thing to remember. And sims, like symbolic operations, we're going to do now. Why? Because we have x equilibrium and u equilibrium, right? And from that we have, or we need to find right? Again, same goes for B, C, D, right? We want to find the matrices of the state space representation, okay, of our, you know, linear dynamical system. Okay, this is x and u, right? And this is just f, right? This is it. Okay, so it may look complicated, but it's not, right? So this is given, right? This is given. Okay, again, maybe I should say something. Sorry, sec. Yeah, again, linear terms, second order terms, constant terms, and 2 input terms, right? All right, so maybe you like to use some simplify command, right? And you need to use Jacobian, right? Here I'm just doing this operation, or maybe this operation, sorry, this operation, right? Asim, and it's a symbolic, right? Again, it will have x and u terms, right? And then substitute for those x and u terms in your symbolic matrix the equivalent point. And these are the numbers. These are the numbers that we know, right? And then obtain your A matrix as double type, okay? And again, same for B, right? For B, what you do is this is it, and then substitute your equilibrium point. Okay, and obtain your B. All right, after that I'm going to try to wrap it out quickly. Now what you have is this: you have a linearized plant. So design a controller, design K, right? Design a controller. Okay, just to design a quick controller, I would recommend you to use mix synthesis, right? Because the syntax is like really simple, and it would allow you to have a quick design. And here V1 W1, right? W1 make weight, and this is like in low frequency, this translates to that in low frequency have 1, and in 3 radian per second have 0.1, and in high frequency have 0.01. This is a low pass filter, right? So this I also explain make weight function to you, right? And just look at the body plot of it just to see if that's really a low pass filter, because it's sometimes easy to make mistakes on those terms. And then look at the evaluate frequency and look at the zero frequency just to see if it's equal to 1. If yes, it would imply that it's unity DC gain, and you might like to have that, right? Okay, so some sanity check over there. And this is your control design part, just the one line. Okay, and here your plant, right? And Statespace form. Okay, and you will have 3 filters: one for tracking error, one for control input signal, and one for output. Okay, and if you don't like to have some weight for your output signals, for example, you can just put empty brackets. Okay, all right. So identity means that not only for some given frequency range, but for all frequency ranges, right? Try to minimize our control signals and also our output signals, right? Okay, I just tried that, right? And I get some control signals. Controller K, right? Okay, now it's completed, and you can of course look at the sigma plot of your closed loop, and closed loop meaning W, U, Z, Y, and P generalize, and gain from exogenous inputs to objective terms. You want it to be minimized, right? Okay, so this is the whole reason of control design, or whole objective of. Okay, and this is simulink, right? So first of all, I'm just generating reference signals. Okay, all right, and I'm just applying a simple disturbance, okay, in a pulse form just to see what happens. Okay, and this is our control, right? This K here embedded in that state space block, and this is here K outputs small signal part, and we need to add U equilibrium or steady state component of input signal, and then we will have U large signal, and this block is not output signals. Yeah, this is our nonlinear dynamical system, right? Give me X and U, and I will give you X dot. Okay, this is it, right? This is X dot, and you need to, and this is integrator, you need to supply X equilibrium as initial condition, and here this is X, right? but you need to, you know, you like to find small signal part of it, and if you have large signal, to find a small signal part of it, just subtract the steady state component of it. Okay, all right, and just since we have that type of linear relation between output and state, and small signal part of our output, right, have that form. It's like simple, right? This is, and by the way, our C matrix is something like this. Yeah. Okay. So this is in the block. Okay. And the nonlinear dynamical, you know, equations are in this block, and we have talked about that. Okay, so this is the whole problem. Okay, and then you look at the output signal and error signal. Okay, now we are going to look at the implementation, and now we're going to look at the